All right, hey everybody. Today is a big day because we are going to take our first look at parametrized surfaces. We are graduating from curves and moving up to the big leagues. So without any further ado, let's jump into it. So first of all, I want to give an intuitive definition of a parametrized surface before we give a much more formal definition. And this is going to build off of our intuitive understanding of a curve. And I'll focus on a curve in three-dimensional space right now. So intuitively, right, a parametrized curve was really a function, right, this capital X, so this vector-valued function from an interval into R3, right? And even in this intuitive understanding, there's a few things that I just want to highlight or unpack here. The first is that this interval, right, this is a subset of R1, and with a parameter t. I'll actually write this down here. Right, so this was a subset of R1. Right, subset of the real number line. It had a parameter t, was our standard parameter, though sometimes we used s or possibly something else, but the usual parameter that we had was the parameter t. And not only is it a subset of R1, but we've always drawn it as an interval or a connected subset of R1. So let me include that as well. Right, so this should be a connected, I almost left myself enough room there, a connected subset of R1. Right? And that means that even though I've typically drawn it like this as a closed interval with endpoints, I could also consider other i's, right, or other potential intervals could be things that go from A to B, things that go maybe like a half open interval, A to B. You could also have a parametrized curve that's defined all the way from negative infinity to infinity, something like that. But typically, it's a connected subset of R1, aka an interval, either open or closed or half open or infinite or what have you. So intuitively, then, if our parametrized curve was a function from a subset of R1 into R3, then our parametrized surface, intuitively, is going to be a function from a subset of R2 into R3. All right, and so our subset of R2 is typically going to be, the letter that we'll use to represent this will be a capital letter U, right? And so this U will be a subset of R2. It'll be a subset of R2, and our parameters that we use, right? We used the parameter t when we were talking about curves, and just sort of by convention, our parameters for our set U will be U and V. So if I'm looking at a subset of R2, right, then I'm going to consider this subset of R2 as living in the UV plane. And every single point, right, will be a point of some kind of u comma v, right? And so it will be a function from this into the xy plane, and therefore we could write this as x of uv equals, and then it would be x of uv, y of uv, z of uv. Right, so we'd end up with three different coordinate functions, each in terms of u and v. All right, so here we have a schematic in which we've drawn a subset u. We have our map x, and it's going into three-dimensional space, sort of mapping onto the surface that we have drawn here. And intuitively, that's a great understanding. But unintuitively, it'll run into some problems. And so we have to be a little bit more precise. The biggest leap that we're going to have to make, at least initially, in going from R1 up to R2 or going from curves up to surfaces, is the idea that this set, this domain set U, can be a lot weirder unless we sort of specify what it is that we are talking about. Right? So in particular, a connected subset of R1 has got to be an interval of some form. There's not too many weird subsets of R1 that are connected. But it's possible to have weird subsets of R2 that are connected, right? So instead of having our U look like this, right? Instead of having our U look like this, what if our u, and let's even move over here a little bit, what if our u had some weirder shape to it, right? So instead of having it just be a nice sort of rectangle like we had drawn there, what if it sort of looks like this and sort of comes to a point, right? Some weird shape like that, or maybe just to make it look a little bit more normal. What if our u was some weird shape that looks like this? Is that a problem, right? Does having a long point like that make it a problem? What about if it looked like this and it was a sort of two-dimensional space, right? A subset of R2, and then we sort of connect it by a very thin neck, right? Even like a curve, and then to another piece here, right? Is that a problem, right? This is a subset of R2. It's a subset of a collection of points in R2. And we consider each of these as filled in. But this piece of it is really more like a curve than a sort of thick, bulky subset of R2. So is that a problem, right? There's all sorts of different things. Like what about, here I just filled this in so it looks sort of like a dumbbell, but what if I didn't fill it in? What if it was literally the set that was this curve, connected to this curve, connected to this curve, without any thickness to it, right? And that was my set U. Is that an allowable set to have? That's connected, but it's weird. It's got these holes in it. So we want to be a little more careful in how we define our set U, and at least for now, just to sort of make a blanket statement that will keep us from getting any sets U that are too weird, I want to make sure that my set U is connected, right? So it doesn't have disjoint pieces. It's connected, and I want to say that U is open. Right? So what happened before couldn't, or in my previous weird drawings, couldn't necessarily happen here, right? And for example, in order for my set to be open, it would need to have no boundary to it, right? So all of my outside pieces here would have to be dotted lines, and so on and so on. So it would have to just contain this piece in the interior of this set. Right, so if I'm looking at open subsets of two-dimensional space, then I at least have a little bit of a handle on how nice or how weird my set U can become. All right, let's see an example using just this intuitive idea, this intuitive understanding. Let's see an example of this in action. And the first example that I want to look at, an intuitive example where everything will be okay, is in the graphs of multivariate functions, right? So a multivariate function is a function with multiple variables like f of x comma y, and if it's a function of two variables specifically, like this is, then I can write the graph of this multivariable function as a parametrized surface, right? In which my x-coordinate just becomes my u-coordinate, my y-coordinate becomes my v-coordinate, and then the height of the function, my z-coordinate, will become f of u comma v, right? So this is typically how we graph multivariate functions in, say, a multivariable calculus class. Now, as an explicit example, and maybe I should say in this case, right, not to get ahead of ourselves, what we have here is simply this function was defined over a domain D. So if D is a nice enough domain in the ways that we want it to be, then we would get, I guess, U will simply be equal to D. So D, of course, had variables x comma y. It was a domain in the xy plane. U will be that same set, but in the uv plane. So as an example, right, let's take a look at the function f of x comma y equals x squared plus y squared. This gives us our paraboloid, our surface that looks like a three-dimensional version of a parabola. This is a paraboloid that we can graph over the unit disk, and we can consider that to be the set of all points x comma y, where x squared plus y squared is less than 1. Right? So what we would do then is we would write this as a function x of uv, and we're going to have its x-coordinate is just equal to u, its y-coordinate is just equal to v, and then its z-coordinate will be u squared plus v squared, right? That function just with u's and v's plugged in instead of x's and y's. And so this could schematically be drawn as follows. right, my set U, which is drawn in the UV plane, is going to be the set of all points inside the unit disk, right? And so let's try to draw that. Here's my unit disk right here, and so it's just going to be all of these points in the unit disk, right? And so that is going to be my U. Right? That looks a little messy, so I'll actually just draw it like that. So it's going to be the interior of the disk, though, right? All of those points on the inside. And then under this map X, I'm going to get this graph in three-dimensional space. Right? So here's my X, Y, Z coordinates. And the graph, right, will have X coordinates and Y coordinates that take place in the unit disk, but the Z coordinates will be given by X squared plus Y squared. So we'll get that familiar paraboloid shape. Right? And so we'll have drawn it to have this bowl opening, starting with this vertex at the origin. Now, because this was an open set, the boundary here is not included, and so up here, this should really be a dotted opening up here, right? That boundary would not be included. But this will be the paraboloid surface, and this is how we have parametrized this as a parametrized surface. One sort of aside that I want to make here, and we'll come back to this a little later, is that one of the really nice things about starting with parametrized curves is that parametrized surfaces, in a certain sense, can be thought of as being built out of parametrized curves. And now what do I mean by that? Well, at least intuitively, right? Here's my domain in two-dimensional space, and here's my surface that's a result. But one thing that I could do is I could take a sort of one-dimensional curve subset down here, and that specific subset, right, that line right there, will correspond to a line on this surface. And specifically this one, where my U is allowed to range from negative to positive, but my V is just equal to 0. Well, that will correspond to my X ranging from negative to positive, and my Y equaling 0. So I'm actually going to get this curve right here, the curve that sort of dips along under the bowl and then pops up the back. So by looking specifically at this subset, what I get is a curve in three-dimensional space that is a part of my surface in three-dimensional space. And that's kind of cool. And we can do this with other curves as well. Let me sort of point out that if I have this curve up here, right? Again, we can consider that as having a constant V height and U allowed to range. That would probably correspond to a curve somewhere over here, something like that. And if I could draw a few more of these, let me just draw one more. Right, that would correspond maybe to one more curve back here. Right, so by drawing several of these curves in my U domain, I can see where those curves appear as subsets of my surface, and they are simply parametrized curves within my parametrized surface. Like I said, we'll talk more about this later. I'll say that when we have these flat curves over here, so V is a constant and only U is changing, these are called coordinate curves, or coordinate lines. Right? And so we can see how those coordinate lines are mapping to these coordinate curves over here. Kind of cool. Okay, so I want to take a look at an example where things break down a little bit, and I want to talk about why they break down so that in a moment we can talk about how to fix those problems, and that will lead us eventually to our rigorous definition of a parametrized surface. Now, for those of you that have taken Calc 3 recently, this should look a little familiar. This is the example that gives us a sphere using our usual spherical coordinates. Specifically, we have x of u comma v equals cosine of u comma sine v, cosine of u times sine v, comma, sine u sine v, comma, cosine of v. All right, and as a reminder, this gives us spherical coordinates with u and v serving as angle measurements. U will take the role of measuring an angle going around in the xy direction, right? So sort of if this is the center of our circle, our u plays the role of measuring how far around the circle we've gone. And that goes all the way from 0 when we're pointing in the direction of the positive x-axis, all the way around to 2 pi when we are once again pointing in the positive direction, positive x-axis. Now, our v takes the other angle measurement, and that's the angle that goes down, right? Sort of starting up at the North Pole at time 0, and then going all the way down to the South Pole at time pi. So that's a rotation of pi, or halfway around the circle. And so taken together, those two measurements, u and v, can point to any single point on the surface of the sphere by looking at how far around we go and then how far down we go. All right, and so in particular, or sort of concretely, that means that our points u comma v will be in the range of 0 to 2 pi cross 0 to pi. And just as a reminder, that means that our first coordinate u is somewhere between 0 and 2 pi, and our second coordinate v is somewhere between 0 and pi. So our u, our capital U, looks like this rectangle right here, and it's getting mapped to this unit sphere. Now, that being said, let's take a look at some of the coordinate curves that we can compute here, right? And we'll see something kind of interesting. In particular, I want to look at, let's say, 3 of them. Let's start with this coordinate curve going from here to here. Right? This has a fixed height at v equals pi over 2. Right? The u is allowed to range all the way from 0 to 2 pi. So this coordinate curve will have a sort of downward angle at pi over 2, and will go all the way from 0 to 2 pi, which means that this will wrap all the way around this sphere along this equator, or this great circle. Right? And so it will wrap all the way around there. So that is this coordinate curve. If I look at a different coordinate curve, let's look up here, and let's go to, let's say this is 3 pi over 4. All right, well, that means that our angle has gone down to an angle of 3 pi over 4, which means it's down here right around the lower tropic of the sphere, if you want to use that language. And then again, the u will be allowed to range from 0 to 2 pi, so it'll wrap all the way around, and we'll end up with this circle down here. Right, this sort of lower circle, no longer a great circle because it's not circling the equator or an equator, but instead this smaller circle. And finally, if I take this edge up here as a curve, what does that get mapped to? Well, if I take pi as my point, right, from 0 to pi, then my angle going down will be pointing straight down with angle pi, and that's pointing directly at the South Pole. And so as my u ranges from 0 to 2 pi, that doesn't move, right? That point doesn't change. That's still pointed at the South Pole. And so this curve gets mapped to just a single point down here, just that southern pole, that South Pole point right there. And that's kind of problematic. So here we begin to see some potential issues in the definition of a parameterized surface, right? With this parameterization, first of all, this is not an open set, right? This is a closed set. It's a rectangle that includes the boundary. And in particular, along this boundary, I have a problem. I have an entire curve in my UV space, but that entire curve is getting mapped to a single point on the sphere. And it's not like there's an inherent problem with the South Pole of a sphere itself, right? Like every point of a sphere is totally fine. The issue is in this particular choice of parameterization. This choice of parameterization collapses this entire line down to a single point. And that has the potential to be problematic if I eventually want to take measurements on the sphere and compute those measurements by pulling back to the UV plane to do my computations in terms of U's and V's. So potential problems here. And so let's take a look at how to fix this. Our answer is actually going to be to have not a single parameterization describing the sphere, but rather to have multiple parameterizations. And so here's what I mean. Let me choose a nice, easy to see color. What I'm going to do is to define several functions mapping sets in the UV plane onto the sphere. So what I could do first is I could say maybe this is my UV plane, and maybe this is my set U1. This should be an open set. So imagine that this doesn't have any boundary, right? Or I've sort of drawn it like this, but imagine that it's open and I'm just looking at the interior of the set. But this is an open set. Doesn't necessarily have to be a rectangle, doesn't necessarily have to be a circle. In this case, it's this weird blobby shape, but it's an open set, so we're good. So I'm going to take this blobby shape, right, this set in the UV plane, and I'm going to define a parameterization, which I'll call x1, that maps onto a piece of this sphere. And maybe let's go ahead and say that this piece maps onto most of the northern hemisphere, right? So let's say that it sort of maps onto sort of a nice hat for the sphere, right? So we have a parameterization that maps onto a piece of the sphere, and it's sort of covering a portion of the sphere. That doesn't cover everything in the sphere, though, right? Just these pieces up top. So what about the rest of the points? Well, we can add an additional parameterization, right? So maybe I have, in the UV plane, I have a different set, right? Maybe U2. And again, let's pretend this is open, so let's not include the boundary. Let's just look at the interior. But maybe I have a U2 there, and then I have this parameterization x2 that covers another part of the sphere. And maybe there's even some overlap here. If I'm being honest, I don't really care. So maybe x2 maps U2 onto this mostly western hemisphere, right? So there's a lot of overlap here. Right? And that's sort of covering this western hemisphere. And then finally, right, there are still some points that aren't covered. Let's add a final parameterization. Right? So here's another copy of the UV plane. Here is a set U3, right? Again, an open set. Here's a parameterization x3. And that parameterization will map this open set in the UV plane. And let's just say that it covers the rest of this. All right, so it covers all of this stuff down here. So no single point on our sphere is actual, or I should say no parameterization, right? None of these, U1, U2, or U3, is actually parameterizing the entire sphere. Instead, we've broken it up into different patches and parameterized each of the patches separately. And notice, some points are in multiple patches, right? So in some points, like maybe some of the points right here, are in all three patches, right? So they are in our U1, U2, and U3 images for our three different parameterizations. But that's okay. This allows me to take a complicated looking surface, one in which I might not find a nice parameterization otherwise, and break it up into individual pieces. And it allows me to nicely sidestep any potential issue that might come from, right? For example, here, having an entire line in my U set mapped to a single point in my image on my surface. So in fact, this is the model that we will adopt because it will allow us to avoid any potential issues like we might have had on the sphere, keep everything relatively regular, and then by extension be able to perform all of the computations that we'll want to be able to perform going forward. So is it possible to have a single parameterization of or to have our surface parameterized by a single one of these coordinate patches? Yes, but not always. And in some surfaces, we will need to have multiple coordinate patches to get the job done. And I should say, just to say it, each of these individual parameterizations will parameterize a coordinate patch on the surface, and that's the language that we'll use. So that leads us to our formal definition of a parameterized surface, and we should really call it, here it's called a parameterized surface, but I think it's probably better called a parameterizable surface, because it turns out that what we're defining will not actually be the function capital X itself. Instead, we'll be defining that set of points in R3. So a set of points in R3, call it S, is a parameterized surface or a parameterizable surface. If I'm being honest, I'll use both of these interchangeably. If for every point in the parameterized surface, there exists some mapping that gives us this coordinate patch. And specifically, there exists the following. There exists an open set U, and so this is in the UV plane, right? So that's in R2 with coordinates U and V. So there exists that open set U. There exists an open subset of R3, call it V, and then there exists a continuous function, capital X, whose image is in the intersection of V and S. All right, let me explain that just a little bit, because that's, I think, a little confusing. Coming back to this example, it's challenging to define subsets of R3 that are on a parameterized surface, right? When it's easier, and so in particular, it's hard to define a piece of a sphere as being an open set in R3, because typically an open set requires a little bit of thickness, and this sphere, right, is really like the hollow shell of a sphere. It doesn't contain anything on the inside. It's just this two-dimensional surface, like the surface of the Earth. Nothing, we're not counting anything underneath. And so the way we get around this is we define an open set in R3, and then we intersect it with this surface. And what we get is just a piece of the surface itself. Right? So it would be like for our set, I guess, U1, I could define the corresponding big set V1, right? And that would be maybe like all of this. So I have this big set V1. This is maybe an open set in three-dimensional space. But if I take V1 and look to see where V1 intersects my surface S, it will appear just exactly in this upper piece right here. And so that allows me to define this piece up here, this coordinate patch, as the intersection of this open set and this parameterized surface. Okay, so our open set is in R3, and then this image, or this intersection, V intersect S, will be the coordinate patch on the sphere that gets mapped to by our function capital X. And so these are the three ingredients that we need, and we have to make sure that every point on our surface has these three, I guess, associated objects. Cool. And so the final thing that I'll say in this moment is, again, we're going to call each of the individual pieces a coordinate patch. So it's perhaps most easily said that a surface is parameterized or parameterizable if every point on the surface can be found in at least one coordinate patch. And each of those coordinate patches are parameterized by these parameterizations, these x sub i's. And then finally, just to see some consistency in our definitions from curves up to surfaces, we will be talking about surfaces that are of class CK, right? And just like with curves, these will correspond to those surfaces whose functions are of class CK, so whose functions are differentiable up to k derivatives, and that kth derivative is still continuous. So a surface is of class CK if it can be covered by coordinate patches, and each of those coordinate patches involve functions that are of class CK. So going forward, I guess what we can see here is that we definitely have a much more complicated definition than we had in the past. And we'll see how some of the things that we've done with curves extend to new results on surfaces.